Good morning. Happy Tuesday. It's my dad's birthday today, so that's fun for him, I guess. Okay, so just a quick heads up, right? We've got quiz 3 coming up this Friday. Well, it'll be open, same as the others, right? It'll be open from Friday morning until Sunday night, right? But it's only on chapter 6. And I know that feels like, oh, that's so easy. Quiz 1 was on like 3 chapters, right? And then quiz 2 was on 2 chapters. So you can see how I'm kind of zeroing in on what's important. And then, did I say quiz 2? And then quiz 3 is going to be just on the 1 chapter, right? But there's a lot in that chapter. So here, just a quick reminder, quiz number 3, and only because I know that there's a little quiz thingy I can steal, so why not? Quiz number 3 will open on Friday. And I can't remember what time. I feel like maybe at 7 or something, early morning. And we'll close Sunday at 11:59 as always. Okay, it's a 50-minute timed quiz, just as before. The idea being you can use the class time that we have scheduled for doing the quiz on the Friday, but you don't have to, right? You can kind of put it off, especially because material from Thursday's class will be covered on there just briefly, but just one question that I have in mind. But just be prepared for that. Okay, so again, it's a 50-minute timed quiz. You'll notice from the assignments that I've posted, right, that these questions are a little bit more involved. So there's really no point in talking about how many questions, just it's going to be a 50-minute timed quiz. So how much you can do in 50 minutes, that's how long it's going to be. Okay, so I could make one question that takes you 50 minutes to complete, right? So talking about that doesn't make sense. Okay, so good. So quiz 3 is on chapter. Quiz 3 is on chapter 6. And from last week, just as a kind of a review, although we're going to move straight into 6.3 today. Okay, and so is on chapter 6. And so last week we did 6.1, which was kind of a recap of one sample proportions, right? But we also introduced how can we calculate sample sizes, right? And so it was a recap of one sample proportions. And so you can expect to see that again. I know you've already seen questions like that, just to introduce confidence intervals and hypothesis testing. I know you've already seen that on quiz 2. So that'll be nice if you get kind of a familiar looking question, right, on quiz 3. So I'm not afraid to do that, right? Because there is that overlap there. Otherwise, I try to keep the quizzes kind of distinct, right? So that there's not a ton of overlap. But in this case, 6.1 is a repeat of chapter 5. So you can expect to see it again. One sample proportions. What did we do with one sample proportions? We looked at hypothesis testing. We looked at confidence intervals. And we also looked at calculating a sample size. So sample size calculations. So this was review from chapter 5. and this was new. Maybe I should do new. It told me, oh, cool. They did an update where I can just tap my fingers to undo, and now I guess I have to be careful with if I tap my fingers. Okay, so that's the new one. So expect to see a sample size calculation, of course, but also hypothesis testing confidence intervals for one sample proportion. Okay, then we moved on to 6.2, which we finished last week, right? With that video that I posted, we kind of wrapped things up with that big example that we did. So we did 2 sample proportions. And for 2 sample proportions, we do not do sample size calculations. So this is the only time where we do sample size calculations is for 1 sample proportion questions. Okay, and so here we just, it's a lot of work, right? We do hypothesis testing and we do confidence intervals for 2 sample proportions. Okay, so then we're hypothesizing about the difference between 2 proportions. Okay, so that was all last week, right? Okay, so we've done that. Now, what I want to do is kind of give you the layout for this week. Okay. We're going to introduce our second test statistic. So we've seen Z as a test statistic for 1 sample proportion, and then we used it again for 2 sample proportions. Remember, once we had that Z, we knew what to do, right? And so now we're going to introduce what's called the chi-squared test. And so it's a test statistic, and we can apply it to lots of different scenarios, but we will be applying it to 2 different scenarios, right? And so 6.3 is the first scenario, and then 6.4 is the second scenario. Okay. So 6.3 is going to be looking at more than 2 sample proportions, or really more than 2 categories, right? And so we have, and maybe I should just call it what we want to call it, a chi-squared test for goodness of fit. That doesn't mean anything to you right now, okay, but it will, right? And so this is for today. And what we're going to find is that we're only going to do hypothesis testing with the chi-squared test. Yeah. And then the section 6.4 is using a chi-squared test for independence. And so it also only uses the hypothesis test, or we only use it for a hypothesis test. And so this is this week. All right, so we don't know what a chi-squared test is, but we're just about to find out. Okay, so call that kind of the end of the review, or the heads up. Let's call it more of a heads up quiz on Friday, or a quiz this weekend, let's call it, right? And same as before, right? You don't have to upload your work, but if you need me to go back and check your work because you think maybe you entered answers wrong, then you have to upload your work within 10 minutes. Okay, so, all right, 6.3, here we go, is technically called what? Let me just go see here, and I'm going to mark this up so it bumps it to the top. Oops. That's way too long. I guess I can I guess I can write that out. Testing for goodness of fit using chi-squared. So this is chi, and let's just talk about this chi-squared. Okay, so I do want to talk about this because it's really important that you know how to say this, because otherwise people will laugh at you, and I don't want that, right? And so it's really important that you call this chi. Okay, it's a Greek letter, of course, and so here we pronounced chi. Okay, and it's written as kind of a fancy X. Okay, here pressure's on, right? I feel like it's like that, like a large fancy X. Okay, so you'll see, I think here there's less pressure, right? When I wrote it, it's just going to be a kind of a large X. Okay? But it's important that you have the little fancy flourish on there, right, for the chi-squared, or you can just write it out, right, chi-squared. Because notice that we have a little squared, right, or chi-squared. Add the squared. Okay. I shouldn't say add. I think you understand what I mean, though. Add is plus, 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 right? But no. Technically multiplying chi times chi, right? Chi squared. Okay, so what is this thing doing? Well, let's take it back a little bit. Okay, and so what if you've collected data and you have more than 2 categories, right? So imagine if you just have one category, well, then you want to look at, okay, was it, well, one categorical variable, I should say, then you would want to compare the proportion of successes to some number, right? What if you have 2 samples, right? Then you have a proportion from group 1 that you want to compare to the proportion of group 2. But now we have more than 2 categories, right? And so consider categorical data. Consider categorical data with more than 2 categories, with more than 2 categories. Right, and so the example that they use in the textbook is, hey, I wrote on it, so it bumped to the top. Didn't want to do that. There. Okay. So the one that I want to use is this example, or maybe, okay, just to talk about what we're doing, let's introduce this example, but then I had one from the exercises in the back that doesn't have a solution. So that might be good for us to work through, right? Because then you can have that solution. And let me just move this closer there. Okay. So a jury, right, is in a trial, then you are supposed to have a jury that is unbiased, right? And so they don't have any preconceived notions or whatever. And so what we're hopefully able to achieve is we want to have a jury that's representative of the population, right? And one of those representations that we might be concerned with is the racial group, right? And so if we have a jury that's already been selected, right, 275 jurors, then if we know what proportion of the registered voters, so the population, right, so here, this is what the population looks like. Versus what the sample looks like. So then what we can do is, okay, if I know that 72% of registered voters are white in this jurisdiction, right, then, or in this county or whatever we're talking about, right, then I have some expected number of people that are going to be white on the jury, right? If I have 275 people, if it's representative, then I would expect some number of juries or some number of jurors, it's hard to say, to be white, right? Same with Black, Hispanic, and other, which is usually kind of a large group, but anyways. So another way that we could think about it, right, is what if we take a step back and we classified all the questions on quiz 3, right? I don't have it made yet. I have the questions, I just haven't put them together, so I don't know, right? But remember, quiz 3 has 4 possible questions, 4 possible question types, right? 1 sample proportion, 2 sample proportions, or chi-squared, and 2 different types of chi-squared, right? But let's boil it down to just 3 categories, right? 1 sample proportion, 2 sample proportion, or chi-squared, right? Because we haven't seen the others, so let's just boil it down. Or consider the question types on quiz 3, right? And so quiz 3, we can have 1 sample proportion, we can have 2 sample proportion, or chi-squared. Okay, and maybe I'll clean that up a little bit. There, chi-squared. Okay. Let's say, just for example, right, let's say that there are 9 questions. Sure. Now, I'm not committing to that. That's probably, honestly, a little bit too many, but we'll see. There's some easier questions, right? So let's say there's a total of 9 questions. There's a reason I chose 9, to make things a little bit easier. Okay, so let's say I have 9 questions, okay? And I have 5 questions from here, and I have 3 questions from here, and I have 1 chi-squared. That doesn't really make sense. It's just an example. This is all fake. It's not real, right? But it gives us something that we can kind of get a handle on. Okay, so now, what if I asked you a question such as, okay, are the questions evenly distributed across the types? What would you say? Probably no. Why? Right? What's your brain doing to get there? Your brain is going, well, if I have 9 questions, then, and 3 categories, I should see 3, 3, and 3, right? And so a potential question. The question might be, are the question types evenly distributed across or in the test? Are the question types evenly distributed? And I just realized something. I'm going to have to tweak these numbers, but just a second here. Evenly distributed. Question mark. I'm going to have to change this to maybe something bigger so that we can kind of do better comparisons. So maybe let's change this to a multiple of 3 because that's easier. Let's change this to 30. And let's change this to 15. Hold up, maybe even 17, right? Make it really obvious that these types, there's some alarm going off in our head that says, no, these are not evenly distributed, right? And so if I have 30 minus 17, I have 13 left to play with. And so what if I make this 7 and 6? Okay. Your brain say no, right? Will likely say no, they are not. Why? Right? Because if they're evenly distributed, now I've tweaked it to 30. Sorry about that change, guys, but it just is easier to deal with, right? And so if I have 30 with 3 different categories, I expect to see 10 in each category, right? And so why, with 30 questions total, and 3 types, we expect to see, and we would be okay with like 10, 11, and 9, right? That's roughly distributed, roughly evenly distributed, right? And so we expect to see about 10 counts in each type. So we expect to see about 10 questions for each type. For each type. But we see, I do that. My brain just kind of smushes words together. It's not great. But we see the most glaring category of 17, right? But we see that there are some categories that are further from 10 than we would like, right? But we see the categories are further from 10 than we would like. Okay. Right, because I'm expecting to see 10, 10, 10 for a total of 30, right? Or about 10, roughly 10, right? We're flexible, but also, you know, not a huge deviation from 10. Okay, so your brain has essentially developed this chi-squared, or half of it at least, the main idea of the chi-squared. Okay, and so here, right, we have these observed counts, and then we have these expected counts. So I want to highlight these expected counts. Okay. So here we have the observed and the expected counts. Okay, so the chi-squared is going to measure the distance between the observed and the expected counts. It does a little bit more than that, and I'll show you what, right? But the idea is the same, right? So it's going to give you some numerical measure of that distance. Okay. So the chi-squared will give us a numerical measure, will give us a numerical measure of how far the observed counts are from the expected counts, of how far the observed counts are from the expected counts. Okay. What's interesting is you could break this information, you could break it down into a 1 sample proportion question or even a 2 sample proportion question, right? But if we want to consider all 3 categories at the same time, then you have to use the chi-squared, because the chi-squared is one of the categories, right? But if you want to know, are more than 50% of the questions 1 sample proportion questions? Well, 17 out of 30 is your sample proportion. What's your hypothesized proportion? You want to test it against 50%, 0.5. You know how to do that, right? Is there a significant difference between the 2 sample proportion questions and the chi-squared questions, or the number of these questions, right? 7 over 30, is it significantly different from 6 over 30? You know how to deal with that question, right? And so you've already dealt with those questions, and now we're looking at the overview of all these categories together. Okay. Overall, does the sample behave as I expected it to? And that's why we get this term goodness of fit, right? Does my sample, does it fit what I expected? Good. And I know it sounds silly, but goodness of fit is a term that we use quite often in statistics, and it's funny because it's really improper, but it's something that we've adopted, and so it's something to get comfortable with. But it's this idea of, okay, how well does my sample match what I'm expecting? Okay. And so the chi-squared goodness of fit test gives us a measure or tests whether our sample or our observed counts are significantly different from our expected counts. Okay, so the chi-squared goodness of fit test tests, there's no other way to say it, it's a hypothesis test, so we're going to be testing stuff. The chi-squared goodness of fit test tests whether our observed counts are significantly different from our expected counts. Yeah. So what happens if our expected counts are not evenly distributed? Although that is a common case, right? Are these groups, are they all the same? Are they evenly distributed? Or is there something else going on here, right? And so, so the example that we started with, the jurors here, right? If we have some proportion, right, from some sample that we have that we're expecting, right, then we can calculate those expected values, right? So if we have expected proportions, we can calculate the expected counts. Okay. So if we have expected proportions, we can calculate the expected counts. What did I technically do here? I took 30 times 1 over 3, right? 1 over 3, I have the number of categories, 1 over the number of categories. That's the probability, the expected probability of being in one of these categories, right? 1 and 3. And then if I multiply that by the total, then I get 10 across the board, right? So part of our work is going to be finding these expected counts, okay? Because we have counts originally that we want to compare to other counts. And so we can calculate the expected counts. And maybe what I'll do is see if I'm going to blow this up here. Whee! Whoops, not too much, maybe. Okay. So then I can find the expected counts. If I have a sample size of 275, right, and I expect the proportion to be 0.72 from the population of registered voters, right, then I would take 0.72 times 275, right? And so, and maybe what I'll do is I'll just kind of bump this down just a smidge here, right? And so recall that P hat is the expected proportion or sample proportion, or maybe I'll just use P is X over N, right? Where X is the count. Oops. So then if I multiply this N over, then I get X is P times N. So now if I have a proportion and I have a total sample size, but your brain probably already did this, right? And so we don't need the formulas, but I always find that it's nice to kind of confirm my brain ideas with formulas. So the expected counts are going to be 0.72 times 275. And maybe I'll just show my work here, 0.07 times 275. Oh, I'm gonna run out of room so fast. Tried to make it bigger, but I made it smaller. Okay, there. And then 0.12 times 275, and then 0.09 times 275. Just like we've seen before in the probability section, right? We have to add to 275. Now there's going to be some rounding here, but as long as you kind of make sure that you're rounding to 275, then you're safe. Okay, we're allowed to have decimal places in our expected counts. Okay, so E is usually how we denote the expected counts. So once we've done these calculations, let's see here, So we have 0.72 times 275 is 198. Whoops, should probably write it underneath. 198. 0.07 times 275 is 19.25. Don't round any values here, right? We're allowed to have decimal places because these are just expectations, okay? 0.12 times 275 is 33. And 0.09 times 275 is 24.75. And of course, if I add these all up, I should get to 275. Let me just check here. Plus 33, plus 19.25, plus 198. Ta-da! I'll put a little check mark there to make sure that I see that I did it. Okay. Do not round expected counts. Okay, so you want to keep those decimal places. They're just expected counts. They're not real counts. Okay. The reason being is, so the 0.07 is clearly not strictly 0.07. It's probably something else, right? And so we're trying to match our population, right? So we're expecting 19.25 Black jurors on the team, I guess, on the jury. Okay, so from here, right, we get a pretty good sense of what's going on, right? But it's hard for our brains to compare to 198 as well as 26 to 19.25 and 25 to 33 and 19 to 24.75. Some of those I'm okay with, right? We're okay with. And some of them I'm kind of like, oh, okay, that's a little bit weird, right? 25 to 33, for example, I'm a little bit, oh, that might be a little bit too much, right? And so the chi-squared actually gives us a numerical measure that we can use, okay? So what we're gonna do is, instead of building up the formula, I just wanna give it to you, okay? And so I'm gonna steal it from the textbook, otherwise I'll write it out wrong. Okay, so they do talk about where it comes from and all that fun stuff, but that's not the formula that I wanted. Dang. Okay. So let me just okay, fine. Sorry, guys, let me just, I'm gonna write this out in more proper notation. Okay, and so the chi-squared is going to be the sum, and I'm going to use O for observed and E for expected. Okay, and then the null count is the expected. The null hypothesis, right, is this sample behaving as I expect it to, right? And so that's why we call it the null count. Okay, so the chi-squared is the sum, the sum of the observed minus the expected. And then I'm just going to go ahead and divide by the expected here. Okay, but it's the sum of the observed minus the expected squared divided by the expected. And the reason I hesitated a little bit, not that it matters to you so much, but it's because the standard error is the square root of the expected. So we take the observed minus the expected, and then we divide it by the standard error, which brings us back to kind of a Z-score, or it is a Z-score, it is a standardization. But I'm skipping all of that. It's all in the textbook, right? And it walks you through it, right? Read the textbook if you are interested in knowing where this came from. But we're not going to talk about it here, mostly because we're a little bit tight in our schedule, so we don't really have time to talk about it. So all we need to know is, okay, so this chi-squared does basically an elaborate thing, right? That our brains already were doing, right? And so we take our observed count, and how far is it from our expected count? And then we square that, right? And then we divide by the expected count, because you see you have a different number of expected counts, so that should play a role probably, right? And then we add all those up. We add those up for each of the categories. Okay, so for the example above, right, let's do this calculation. But also, before we do, a large chi-squared tells us what? It tells us that the distance between the observed and the expected, taking into account even the spread, right, is large, right? Whereas if the distance is small, then this is going to be a small number, and if we square it, it becomes positive, right? But we amplify those large distances by squaring. And then dividing by the expected count doesn't really do anything. It just kind of divides by whatever the spread is. And so large values of chi-squared tell us that there is likely a difference there. Okay, so large values of chi-squared tell us there is likely a difference between the observed and the expected. And the expected counts, let's see. So in that example from the textbook, right? Let's steal what we had here, and I'm going to copy this, but then I'm going to remove it because I just want to steal, right? I'm going to steal my categories: white, black, Hispanic, and other. Now I don't need the totals anymore. I needed the totals to find the expected counts, but really now I'm just focusing on my categories. So the observed counts are 205, 26, 25, and 19. And the expected counts — 198, 19.25, 33, and 24.75. Oops, bungled it. Okay, now I'm going to delete that. Okay, so to calculate our chi-squared, what are we going to do? Our chi-squared, we can calculate it as, so it is a sum, so we're going to do this for each of them. So what you could do is you could calculate each of the Z-scores, they are Z-scores, underneath here, and then add those up, or you can do them all in a row like I'm about to do. but it doesn't matter. It's 205 minus 198 squared divided by 198 plus 26 minus 19.25 squared over 19.25 plus 25 minus 33 squared over 33 plus 19 minus 24.75 squared over 24.75. Now, I really hope that I can find this calculation because I really don't want to do it by hand here. That would be kind of a waste of time for us. But of course, you would do those calculations. And what we should find, let's see if I can find it. Where I should have jotted it down. I think chi-squared is 5.89. Chi-squared is 5.89. And that's stolen from the textbook. Stolen from the textbook. So maybe just when you get a chance, just confirm that. I'll confirm it as well, or I'll try to remember to confirm it. But let's just go with that. Okay. So now chi-squared is a test statistic, right? So we are doing a hypothesis test, and we've already sort of established our hypothesis, but unlike the one sample and the two sample proportion questions, we're not going to be talking about specific parameters. We're going to be talking, but we can, usually we talk about this sample follows this distribution, right? And so the goodness of fit can take on a couple of different null hypotheses, right? And so this gives us chi-squared gives us the test statistic for testing the null hypothesis that the distribution of jurors, right, is representative of the population. The distribution of jurors, and maybe I'll outline this as step one. State the hypotheses. Hypothesis, the distribution of jurors is representative of the population, right? That's what we're assuming. We have to assume that the distribution of the jurors is representative of the population, right? And so so that's where we start, although maybe we have some idea, right? Or maybe we just have to check it, right? We're not hoping to reject the null hypothesis in some cases, right? Some cases we're just making sure that we can't reject the null hypothesis, right? But the alternative hypothesis is that the distribution of jurors is not representative of the population, right? And so, oops. The distribution of jurors is not representative of the population. Okay, so thinking about kind of a one sample proportion question or even a two sample proportion question, then we state our hypotheses, right? They're just about, in general, what's going on with compared to the population. And then in step two, what do? We do the test. But now, because we're doing a goodness of fit test, right? Is it representative of the population, right? For a goodness of fit test, step 2 is do the test, right? And this is where we calculate the chi-squared test statistic. And from above, we found that chi-squared in this case is 5.89. Okay. Step 3 is find the p-value, right? And so what are we actually asking? Well, 5.89, we know that a large chi-squared is going to be considered significant, right? The distance between the observed and the expected is significant, right? Significant means that we can reject the null hypothesis in favor of the alternative, right? And so, so how large does my chi-squared need to be? Well, this is the first time that we're seeing it, but it's not the last time that we're going to see it. It depends on a parameter called the degrees of freedom. Okay, and so step 3 is find the p-value. Okay, or in this case, for chi-squared, we typically just find the critical value. We could have done this for z-tests as well. We don't have to use a p-value. I'll show you, and then you can kind of look at the difference. Okay, but for chi-squared tests, we will use the critical value approach. We will use the critical value approach. Okay. But before we can do that, so we don't find a p-value, although we sort of could. We could find a range for the p-values, but instead of finding the p-values, we're going to find the value of chi-squared. So anything larger than this chi-squared will be considered significant, right? And so what happens here is we find that the critical value approach says that any value larger than this, or maybe I should say any calculated chi-squared value, any calculated chi-squared value larger than blank, and that blank is the critical value. Will be considered a significant chi-squared, right? Or will be considered significant. Significant means reject H naught. Yeah. Or you have enough evidence to reject H naught, right? Okay, so what we do, at least classically, is we use the chi-squared distribution. Okay, so the chi-squared distribution, to find the critical value, we use the chi-squared distribution with, and I feel like it's C, which is the number of columns or categories, with degrees of freedom equal to, and we don't know what degrees of freedom are yet. I feel like we haven't talked about them, but equal to the number of columns or categories minus 1. Right, and so what we say is we say degrees of freedom is C minus 1. C can be columns or it can be categories. It's technically categories, but that's okay. Okay, so that doesn't mean anything. The reason we need the degrees of freedom is because the shape of the chi-squared depends on the degrees of freedom. Yeah. We need the degrees of freedom. And I'm just going to abbreviate that to DF now and not, I'll probably never write degrees of freedom again. Or at least today, we need the degrees of freedom because it determines the shape of the chi-squared. Because it determines the shape of the chi-squared. For example, and I'm going to steal this from the textbook here because they have the different or some different shapes. Well, I don't like these, but okay, in general, it's going to look like this. So I've got my axes here, and it's in general going to look like this. So it's a skewed distribution, and maybe I should do that a little bit better, right? And so it's a distribution where chi-squared is skewed to the right, right? And it can only have positive values, which is fine, right? Because what are we technically modeling? We're technically modeling categorical data, so counts, right? You can't have negative counts. You can't have negative proportions, right? And so here, right, it can only handle positive values, only handles positive values, right? Such as counts or proportions or probabilities, etc. Okay, so it's going to be skewed to the right, and depending on the degrees of freedom, we're going to get a slightly different shape. And I feel like it gets higher with the higher degrees of freedom and kind of more compact, and then it smushes out. So what we're going to do is we're going to find a critical value by setting the area in the tail. So for chi-squared tests, we're always going to do a one-sided p-value. In fact, it's always going to be a right-tailed test, or yeah, right-sided test, I guess. For chi-squared tests, we always do a one-sided test, more specifically, a right-sided test. We always do a one-sided test. Oops. Specifically, a right-sided test. Is the distance between the observed and the expected, is it larger than what we're expecting to see? Okay, and so what we have is we have this distribution of chi-squared here. So here's my chi-squared values. And what we do is, to use the critical value approach, we force this area in the tail to be the alpha level. To use the critical value approach, we force this area to be the alpha level, right? Typically 0.05, right? So if we force that area to be 0.05, and then we find the corresponding chi-squared. And I'll denote it with a little crit to denote that that's the critical value. So we force that area to be the alpha level, so 0.05 typically, then find the corresponding chi-squared crit chi-squared critical value. Of course, software does this for us, but we can use a table, which I have had hidden on our Moodle page. And let's see here. Let me just go to Moodle here. I can't remember if I actually unhid this. Because I'm here, but that's not our page. It's my other section, but I should have done theirs already. Oops. And then chi-squared table show. Okay. So chi-squared table, there's one in the back of the textbook, of course. And here, so this one is from the back of the textbook, and it does a really good job of explaining how it all works. And so we're just going to skip straight to table. In fact, I don't think I have this in my going to bring it in. Okay. Well, it turns out I had it somewhere. I don't know. From the name it gave it. So the chi-squared table, if we scroll down, so it has lots of examples and it explains that the shape kind of differs, right? And so depending on the degrees of freedom, so if we have 3 degrees of freedom, or if we have 2 degrees of freedom, right? Here's what it looks like with 3 degrees of freedom, 2 degrees of freedom. Let's see here, 5 degrees of freedom, 7 degrees of freedom. So it seems to be moving a little bit more towards the center, so eventually becoming normal, which is opposite from what I said, but just read this and you'll be fine. Okay, so the chi-squared distribution is going to have some degrees of freedom. So in our case, we had 3 categories. Right, so how many degrees of freedom do we have? We have 2 degrees of freedom. So in our example, or sorry, I need to talk about the jurors. We had, sorry, I skipped back and forth, and that's not cool. 1, 2, 3, 4 categories. Right. So in our example, the jurors example, we have 4 categories. Therefore, our degrees of freedom is C minus 1. Degrees of freedom is 4 minus 1. So in our case, the degrees of freedom is 3. Just as a heads up for Thursday, we're still going to use the chi-squared, and the idea stays the same, but how we find the degrees of freedom is going to differ. But besides that, everything else stays the same. Oh yeah, here, nice. Okay, so what we're doing is we're looking at one variable, right? The jurors. And then we're looking at the distribution of the jurors within that one variable. Awesome. And then next day, we're going to say, well, what if I want to look at two variables and how they behave, right? So now I'm going to have columns and rows to deal with. But besides that, nothing really changes from today to the next day. Okay, just kind of more advanced techniques. Okay, so in this case, we have 3 degrees of freedom. So using our table, oops. Where did it go? Oh, using our table, all right, I'll show up to 5 degrees of freedom. How many categories would you have to have 5 degrees of freedom though? 6 categories, yikes. And then it goes on and on and on and on, right? So that's crazy. So for us, we have 3 degrees of freedom. So what we're going to find is that we're restricted to this one line. Okay. So the upper tail, that's going to be your alpha level. Okay. Upper tail is going to be the alpha level. So here's where you can say the default is 0.05, right? And so the default is still 0.05. So here, right, if I use oops, didn't want to be in the highlighter, right? If I use an alpha level of 0.05 with 3 degrees of freedom, that tells me that my critical value is 7.81. Okay. So my chi-squared critical value is 7.81. This means that in order to have enough evidence to reject H0, I have to have a chi-squared larger than 7.81. Okay. What else could we do? So the C is the number of categories. I got a message here. There. What if we wanted to use the p-value approach, right? So I don't dictate what the 0.05 level is, right? And then find the critical value. If I wanted to use the p-value approach, we would take our calculated value and place it somewhere between these, within these values. So notice that it increases as we move out, okay? And so here, let's say, but I should state my conclusion here first. This means that if our calculated chi-squared is larger than than the critical value, then the critical chi-squared, we have enough evidence to reject H0. We have enough evidence to reject H0. Your conclusion then stays the same. Once you have a conclusion, okay, if I have enough evidence to reject H0, then what does that mean in terms of my question, right? And so in our case, right, we had, and I'm going to steal it from here because they've drawn it way nicer than I do, obviously, with software. Okay. So what we found was that this here is the chi-squared calculated was 5.89. 5.89 is that calculated chi-squared. Okay, now what we found is that the critical chi-squared is 7.81, so somewhere here. So the chi-squared critical is 7.81. Okay. So, right, chi-squared is increasing as we move out here. So just like in the z-score situation, right, we had this, we could have used the critical value approach for z-scores too, right? We can say, okay, if it's beyond 2.1 or something like that, then I'm going to have enough evidence to reject H0, right? Here it has to be beyond 7.81, but in this case it's not, so I don't have enough evidence to reject H0, which means what? In terms of the jurors, it means that there's nothing to say that the jurors, right, or the distribution of the jurors is significantly different from the population, right? So in this case, oh, and maybe I'll say step 4 is your conclusion. Since our calculated chi-squared was 5.89, is not, and maybe I shouldn't say, I won't start it with in this case because I just kind of picked up at the problem, but is not greater than our critical value of 7.81. Notice how I talk about what the values are, right? That's just proof. You've already found these values. Why not look them off, right? So since calculated chi-squared of 5.89 is not greater than our critical chi-squared of 7.81, we do not have enough evidence to reject H0. Therefore, right, so now instead of comparing my p-value to my alpha level, I'm going to compare my calculated value to my critical value, but then the conclusion stays the same, right? You either have enough evidence to reject H0 or you do not. Right, so we do not have enough evidence to reject H0. Therefore, the distribution of jurors is not significantly different from the population, or the distribution of jurors is representative of the population. Right, if I can't reject this, that's my final statement. Therefore, the distribution of jurors is representative of the population. Oops. Oh, I want to do multiple points there. Okay, good. I want to just make a quick note because I was talking about the p-value approach, right? So we could also use the p-value approach. Note, we could use the p-value approach by placing our calculated value somewhere on where it belongs on the line in the table. By placing our calculated value, or our calculated, can't spell anymore, chi-squared, where it belongs on the line in the table. So what does that look like? Well, copy. Okay, let's see here. Clean this up because this is from before. Right, so now I still have 3 degrees of freedom, but I'm trying to take my calculated chi-squared, which in this case was chi-squared equal to 5.89, right? 5.89, if I start here, right, 5.89 would fall somewhere between these two values. Right, so here, 5.89. And I don't do any shifting or anything because software would do a better job of that than I can do, right? Because I don't have a uniform distribution, so I've got that curve to deal with, and that's making a mess, right? But what I can find is that the corresponding p-values, so this tells me the p-value is somewhere between 0.1 and 0.2. Notice that you have to read them backwards. So we find the p-value corresponding to chi-squared equal to 5.89 is somewhere between 0.1 and 0.2. So whichever one you prefer, go for it, right? 0.1 and 0.2, is that less than 0.05 if that's your alpha level? No, right? Doesn't matter. That whole interval is above 0.05, which you can see here, right? So what I want you to do is kind of think about that. What if I wanted to use a critical value approach for previous questions that we did, right? You can do that. But anyways, I'm out of time. If you have any questions, let me know. Otherwise, I'll see you on Thursday. Stop this here.